Alright, so now let's consider the application of the Galerkin method to a specific problem, in particular the Dirichlet problem. So let's set up the problem. So let's consider a open rectangle in the plane. Okay, which we denote by omega. So omega is a set of points x, y in R2 with the property that absolute value x is less than 1, the absolute value of y is less than 2. Okay, and then we're looking for a solution of the form u. So we want to find a continuous function u, okay, which is defined on the closure, it's like of this. So that basically means that in addition to, absolute value of x being less than 1, you actually want the equality as well, right? So it includes the boundary of this rectangle. So this is defined on the closure, omega bar, such that sort of the Laplacian applied to u equals to 0, and uxy, and so this is in the interior, omega, and uxy is equal to, say, x squared plus y squared, which is the boundary condition on the boundary of omega. Okay, so this obviously is a linear operator acting on u is equal to some right-hand side, right? So you can interpret this as sort of a linear operator Lu equals to F, right? Where we define L and F as follows. So, all right, so it's not such a big deal, obviously, to think of the differential equation part of this as a linear operator, but we're also going to think of the boundary condition as a linear operator. Okay, so Lu is going to be given as follows, right? So this is going to be the Laplacian acting on u, and u restricted to the boundary. And f is going to be equal to 0 x squared plus y squared. Okay, so basically we're thinking of both, it's like the actual differential equation as well as the boundary condition as a linear operator acting on the solution. It's like equal to some prescribed right-hand side. Okay, so this just denotes, so this is the restriction of u to the boundary. Okay, and it's a linear operator. Okay, so which is a linear operator? Okay, so in order to construct a Galerkin discretization of this, what you want then is to choose a set of trial spaces, basis functions for expanding, it's like the solution, or sort of, as a basis, it's like for considering candidate solutions to u. Okay. So want to find sort of basis functions. Let's call them ui. So it's natural to consider functions that are harmonic. What I mean by that is that that the Laplacian that's like applied to the UIs vanish. Okay, and of course it's like the reason, of course, why you might want to expand. It's like the solution of the Dirichlet problem in terms of harmonic functions is that they automatically satisfy the differential equation, right? So all you really need is to find appropriate combinations of these harmonic functions so that they satisfy the boundary conditions. So clearly, linear combinations of harmonic functions automatically satisfy condition that okay, so just need to pick the CIs, right, to satisfy the boundary conditions. Okay, all right. So one way to sort of construct harmonic functions, okay, is the following observation. So one sort of rich source of harmonic functions sort of comes from the observation that the real and imaginary parts of a analytic function is harmonic. Okay, real and imaginary parts of any analytic function of a complex variable harmonic. Okay, so so an easy way to so easy examples of analytic functions of complex variables include just the powers it's like of a complex variable. So in particular, z to the k, right, is analytic. So let's look at powers of z. Okay, so z to the 0, obviously, and obviously z is equal to x plus iy. Okay, so z to the 0 is just 1, not very exciting. Z to the 1 is just x plus iy, right? Z squared is x squared minus y squared plus 2 xy I, and so on. Okay, z cubed is equal to x cubed minus 3xy squared plus 3x squared y minus y cubed I. Okay, z to the 4 is x to the 4 minus 6x squared y squared plus y to the 4 plus 4x cubed y minus 4x y cubed I. Z to the 5 is x to the 5 minus 10x cubed y squared plus 5x y to the 4 plus 5x to 4y minus 10x squared y cubed plus y to the 5 times that imaginary times I. And then z to the 6 is x to the 6 minus 15x4 y squared plus 15x squared y4 minus 6 y to the 6. Okay. Plus 6x to the 5 y minus 20x cubed y cubed plus 6xy to the 5 times I. Okay, so the reason why I expanded it out so much is because in addition to looking at sort of harmonic functions, I'm also going to try to find harmonic functions which respect the symmetry of the boundary conditions, if you will. Okay, so let me say a little bit more about that. Right, so if you recall, the boundary condition is that you know, it's like u restricted to the boundary of omega is equal to x squared plus y squared, right? So that's the boundary condition we had prescribed. And it's sort of clear that the boundary condition has some reflection symmetry. So the boundary condition right has sort of reflection symmetry. So what I'm going to do is I want to choose, you know, it's like these candidate harmonic functions. Well, they're all harmonic functions, but it's like choose these candidate shape functions. It's like which also respect this reflection symmetry. So I want to pick harmonic functions with the same symmetry. So in particular, that means that we're only going to look for things which involve even powers of x and y. Okay. So I want to look for harmonic functions involving even powers of x and y. Okay. So as an example, it's like you have this x squared minus y squared term. You have 1, right? Okay. So let's look at these. Okay. So u1 is going to be 1. u2 is going to be x squared minus y squared. u3 is going to be, say, this term here, right? X to the 4 minus 6x squared y squared plus y to the 4. And then u4 is going to be the real part at sec of z to the 6, which is x to the 6 minus 15x to the 4 y squared plus 15x squared y to the 4 minus y6. Okay, as I said, it's like any linear combination, it's like of these harmonic functions is going to automatically satisfy the differential equation because they individually satisfy the differential equation, and the differential equation is a linear differential equation. Okay, so any combination, any linear combination sum over I of Ci ui satisfies nabla squared acting on sum of I Ci ui is going to equal to 0. Okay, so again, all you really need to do is to try to find some coefficients. It's like such that that linear combination of the ui's, right, approximates the boundary conditions as best as you can. Okay, so we want to sort of solve for the ci's such that the sum of Ci ui over I is equal to x squared plus y squared on the boundary, at least approximately. Okay. And then again, because of the symmetry, it's like of both the boundary conditions as well as the trial functions, it's like which I've chosen, all you really need to do is to test this on one of the quadrants. So by symmetry, right, we only need to sort of consider one quadrant of this boundary. Okay, all right. So one possibility is to, one way to approximate it's like this boundary condition is to just choose some points it's like on the boundary and check whether that's satisfied. So let's see what happens. So one way to approximate this boundary condition constraint is to pick sort of 4 points, right, on the boundary. Okay. So as an example, for example, we can pick these 4 points, 0, 2, 1, 0, 1, 1, and 1, 2. Okay, so let's sort of look at what's happening here. Okay, so the condition is that x is 1, y is 2, right? So you have this piece of the boundary. Okay, so 0, 2 is this point, right? Maybe let's put a cross there, right? 1, 0 is this point, 1, 1 is this point, and 1, 2 is this point, right? So we're picking these 4 points, it's like on the boundary. It seems reasonable enough. Okay, and we're going to impose the condition that on those 4 points, this linear combination of the ui's, it's like it actually agrees, it's like with the prescribed boundary conditions. Okay, so that's basically what the linear system we're going to have to solve for is, which would then give us the CIs. Okay, so this is an example This is what is called a collocation method. Okay, where you just do a pointwise evaluation. It's like of the something which is satisfied over a continuous interval, right? You also can do collocation in time as well, but here we're doing collocation in space in some appropriate sense. Okay, so anyway, so if you do this, it's like then you get the following linear system of equations. For this, we get the following linear system. Okay. Acting on C1, C2, C3, and C4 is equal to this right-hand side, which is 4, 1, 2, and 5. Okay. So you can solve this, it's like numerically, and the approximate solution C is approximately 1.8261, negative 0.7870, negative 0.04348, and 0.004348. Okay. All right. And then with that, it's like you can check actually what the error it's like in satisfying this boundary condition over the entire interval is, and you can check that for this particular choice of linear combination of the U1s to U4, the error is so the infinity, so the maximum error in the boundary condition is approximately maximum pointwise error is about 0.074. Okay, so that's one way to do this. So another thing you could do is to do some sort of least squares type approach. Okay, so let's see what happens. Okay, so another approach is that you look at is to pick sort of m points on the boundary and sort of formulate this in a least squares fashion. Okay, so so in general, obviously, it's like you might want to choose this so that m is greater than 4. So you have 4 unknowns, it's like in this problem, right? Coefficients C1 to C4. If you pick more than 4 points, then basically, in general, it's like the system of equations you end up getting if you were to try to require that linear combination of 4 basis functions exactly satisfies the sort of the boundary condition, right? So if m is greater than 4, you would have m equations, it's like, but in 4 unknowns. So in general, it's like that system is overdetermined. And in those situations, what you oftentimes do instead is you take this kind of least squares approach, where you try to minimize, it's like the error at those m points. So what we're going to do then is that we're going to take this linear combination from I equals 1 to 4 of Ci ui, right? And so let me denote those points as xi, yi, okay? And I'm going to evaluate them at xi, yi and I'm going to compare it to the boundary data, which is xi squared minus or plus yi squared. All right. So this is the pointwise error you're making in replacing, it's like this boundary condition on the boundary at the point xi, yi with this linear combination of the basis functions. Okay, so then I can square it, and then I can sum this over the i's equals to 1 to m. Okay, so I'm going to then sort of take this, the square of this residual error at each of these I points, it's like, and then I sum it over sorry, this is the residual error. It's like at the ith point, I square it, and then I sum it over all those m points. Okay. So this is sort of a least squares approach to doing things. And again, it's like this is something which you've probably seen before, particularly with linear regression, right? So if you're trying to fit a linear function to many points, right, especially more than 2 points, then one way to do this is you compare, it's like the linear model, right, with the data, okay, and then you take the square of the error and you sum it all up. So here again, it's like you have this linear combination, it's like which is your candidate solution. You're evaluating it at point xi, yi, and then you're comparing it to the boundary data, okay, and this is the difference. So it's the residual error, and you square the residual error, and you sum it over all m points, okay. And and of course, this includes collocation as a special case, right? So this includes collocation as a special case. When m is equal to 4, right? So basically, when the number of points you're requiring, it's like, or minimizing the error for is equal to the number of unknowns which you have. Okay. So anyway, yeah. So this is one way to do it. And in the book, it's like there is a discussion of, well, trying to do this for a large number of points. Okay, so I'm not going to spend too much time going to the details of that. So, but let me just sort of say that, but in practice, right, one tends to take this kind of least squares approach when m is much bigger than the number of unknowns. Well, let me just write this as number of unknowns. Okay. All right. Okay, and then, so that's another approach. And then finally, another approach is a min-max approach. Okay, so let's consider the following. So let's consider the maximum error. Right, so you can look at the maximum error over all the points which you sampled, maximum pointwise error. Oh, sorry. Okay, so this is just a pointwise error, and I want to look at the maximum error it's like you have, okay, over the data, over the points. So this simulates, so that this approximates the maximum error. When m becomes large, right, and of course if the points are sort of spread out, right. So you don't want them to just concentrate on a particular region of the boundary. All right, so this is the maximum error in some sense, right? Or approximation of the maximum pointwise error in satisfying the boundary condition. And of course, it's like what you want to minimize is you want to minimize the maximum error by sort of varying the CJs, okay? Then to pick the CJs, right, you want to minimize the maximum pointwise error. Okay. All right. So that's one other approach. So you want to find the min over the CJs, right, of the max of this. Sorry, that's not what I wanted to say, right? So I wanted xi squared, yi squared. So that's the boundary data, sorry. Okay, so xi squared plus yi squared. Okay, so again, this thing here is a approximation of the maximum pointwise error. It's like which one makes by replacing the actual prescribed boundary data by this linear combination of basis functions. And then I want to minimize that maximum pointwise error. It's like by choosing the CJs appropriately. Okay. All right. So so that's basically yet one other approach. So anyway, so this should give you some idea of how one might go about trying to use these Galerkin type methods to solve a Dirichlet problem, and more generally, it's like other PDEs. Okay. So let me just stop here for now.